Neural Networks Overview. A neural network is a computational model inspired by the structure and functioning of the human brain. Neural networks are a subset of machine learning, particularly useful for modeling complex relationships in data, and are a key component of deep learning. Neural networks consist of layers of interconnected units called neurons or nodes, which process information. These models are designed to recognize patterns and perform tasks like classification, regression, and feature extraction. Key components of neural networks. Neurons, nodes. Each neuron represents a mathematical function that receives inputs, processes them, and produces an output. A neuron takes multiple inputs, features, applies weights, sums them up, passes them through an activation function, and produces an output. Layers of neurons. Input layer, the first layer, which receives the raw data or features. The number of neurons in this layer equals the number of features in the dataset. Hidden layers, layers between the input and output. These layers process the data by learning complex patterns. Neural networks can have multiple hidden layers, which is why deep neural networks, DNNs, are called deep. Output layer, the final layer, which produces the result, e.g. class label in classification or value in regression. Weights and biases. Weights, parameters that define the strength of the connection between neurons. Weights are adjusted during training to minimize the model's error. Biases, additional parameters that allow the model to fit the data better by shifting the activation function. Activation function. The activation function introduces nonlinearity into the neural network, enabling it to model complex relationships in the data. Without activation functions, the neural network would essentially perform linear transformations, limiting its power. Common activation functions. Sigmoid, outputs values between 0 and 1, commonly used for binary classification. ReLU, rectified linear unit outputs 0 for negative inputs and passes positive values unchanged. ReLU is commonly used due to its simplicity and efficiency in deep networks. TAN, outputs values between -1 and 1. It's similar to the sigmoid function but has a broader range. Softmax, often used in multiclass classification problems, outputs probabilities for each class. Loss function, the loss function measures the difference between the model's prediction and the actual output. The objective during training is to minimize this loss. Examples. Mean squared error, MSE, common for regression tasks. Cross-entropy loss, common for classification tasks. Optimization algorithm. Optimization algorithms adjust the weights and biases of the neural network to minimize the loss function. The most common optimization method is gradient descent. Gradient descent iteratively adjusts the weights by calculating the gradient, or slope, of the loss function with respect to the weights. Variants of gradient descent. Stochastic gradient descent, SGD, updates weights based on a single data point at a time. Mini-batch gradient descent, updates weights using a small batch of data points, balancing efficiency and accuracy. Atom optimizer, a more advanced optimization technique that adapts the learning rate for each parameter. Types of neural networks. Feed-forward neural network, FN, and the simplest type of neural network where the information flows in one direction, from the input layer to the output layer, passing through. Hidden layers. Used for tasks such as classification and regression. Convolutional neural network, CNN, primarily used for image and video processing. CNNs are designed to recognize spatial hierarchies in data. CNNs use convolutional layers that apply filters, kernels, to the input to capture local features, for example, edges, textures. After convolution, the network typically includes pooling layers, for example, max pooling, to reduce dimensionality. Common applications: image classification, object detection, and facial recognition. Recurrent neural network, RNNs are used for sequential data, for example, time series, speech, or text, because they have feedback connections that allow information to persist over time. RNNs are capable of processing sequences by maintaining an internal state, which helps to capture temporal dependencies. Long short-term memory, LSTM, and gated recurrent units, GRU, are special types of RNNs designed to overcome the vanishing gradient problem, which makes it difficult for traditional RNNs to learn long-term dependencies. Generative Adversarial Network, GANs consist of two neural networks, a generator and a discriminator. The generator creates fake data, and the discriminator tries to distinguish real data from the fake. These two networks compete in a zero-sum game, improving each other over time. GANs are used for tasks like generating realistic images, deepfakes, and art creation. Autoencoders. Autoencoders are neural networks used for unsupervised learning, particularly in dimensionality reduction and feature learning. They consist of an encoder, which compresses the input into a smaller representation, and a decoder, which reconstructs the original data from the compressed representation. Common applications include anomaly detection, image denoising, and data compression. Transformer networks. Transformers are designed to handle sequence data, especially in natural language processing, NLP, tasks. Unlike RNNs, transformers use self-attention mechanisms to capture dependencies between words or elements in a sequence, regardless of their distance from each other. Transformers have revolutionized NLP, with models like BERT, bidirectional encoder representations from transformers, and GPT, generative pre-trained transformers, setting state-of-the-art benchmarks. How neural networks learn, training process. Forward propagation, input data is passed through the network, and computations are performed in each layer, input, hidden, and output. Each neuron in the hidden and output layers applies a weighted sum of its inputs and passes it through an activation function to produce the output. Loss calculation. After forward propagation, the model's prediction is compared with the actual target, and the loss, or error, is calculated using a loss function. Backward propagation. Backpropagation is the process of adjusting the weights and biases based on the loss calculated. It involves gradient calculation. The gradient of the loss function with respect to the weights is calculated. Weight updates. Using optimization algorithms like gradient descent, weights are adjusted to minimize the loss. Training iterations. Epochs. The process of forward propagation, loss calculation, and backpropagation is repeated for several iterations, epochs, until the network converges, i.e. when the loss stops improving or reaches a satisfactory minimum. Applications of neural networks. Image recognition. Neural networks, especially CNNs, are widely used in tasks like image classification, object detection, and facial recognition. Speech recognition. RNNs and LSTMs are often used for transcribing spoken language into text, like in virtual assistants, Siri, Alexa. Natural language processing. NLP transformers have been revolutionary in NLP tasks such as machine translation, text generation, and sentiment analysis. Autonomous vehicles. Neural networks are used to enable self-driving cars to perceive and interpret their environment, for example, detecting pedestrians, other vehicles, traffic signs. Healthcare. Neural networks are used for medical image analysis, for example, MRI scans, and predicting patient outcomes. Finance. Neural networks are used for credit scoring, fraud detection, and predicting stock prices. Challenges in neural networks. Overfitting. Neural networks with many parameters are prone to overfitting, where they perform well on the training data but fail to generalize to unseen data. Regularization techniques like dropout or early stopping are used to mitigate this. Vanishing gradient problem. In deep networks, the gradient can become very small, making it difficult for the model to learn. This issue is addressed by using activation functions like ReLU and architectures like LSTMs. Computational cost. Training deep neural networks requires substantial computational resources, including GPUs and TPUs, making it expensive and time-consuming. Summary. Neural networks are a powerful tool for solving complex problems in various fields, from image and speech recognition to natural language processing and reinforcement learning. By mimicking the brain structure and learning through data, neural networks are capable of discovering intricate patterns and making intelligent decisions. With advancements in algorithms and hardware, neural networks continue to push the boundaries of AI, enabling new breakthroughs in technology.